everyone. I am SINGH, a BTech third year student of Branch Engineering Physics at IIT Roorkee. Today I am going to talk about superconducting quantum interference device, that is SQUID. This is probably the most widely used quantum device in the world. There are three quantum mechanical effects crucial to understand the operational working of SQUID. Those are as follows: superconductivity, Josephson effect, and magnetic flux quantization, similar to the quantization of the angular momentum of the electrons orbiting atoms. In a superconducting ring, the flux passing through it must correlate to a quantized phase matching like in the green ring. Only quantized values of flux are allowed to pass. Superconductivity. It was discovered in 1911 by K.H. Owens. While trying to measure the residual resistivity of mercury at liquid helium temperature, he found that below a certain temperature the resistance becomes zero. Not only in mercury, he found similar effects in other materials also and called them superconductors. This allowed changes to move with perfect efficiency without energy loss with zero resistance in the lattice. Another interesting discovery regarding superconductors is the Meissner effect, where below a critical temperature, superconductor doesn't allow any magnetic field to penetrate, hence behaving as a perfect diamagnet. BCS theory and Cooper pairing. The first microscopic quantum theory of superconductivity was given by Bard and Cooper and Schoffer in 1957. So let's see how BCS theory describes the superconductivity. It involves two electrons bound in a Cooper pair coupled over the order of several hundred nanometers interacting in the lattice that is based on the order of just a few nanometers. When an electron moves through the lattice, it disrupts the positive ions near to it, creating a ripple, and when the next electron moves into this region, it is attracted to the displaced positive ions. The attraction between these two electrons creates a binding energy. The temperature must be low enough not to disrupt this binding. The effect can be arrested in the Feynman diagram, where the phonon symbolizes the lattice vibration. Here we can see how the disturbance in the lattice due to one electron attracts another electron towards it, forming a pair. Josephson effect. In 1962, Brian Josephson theorized an effect that can happen between two superconductors connected via a weak link like a dielectric or a metal. This is the representation of such a Josephson junction, showing two superconductors separated by an insulating layer. This diagram represents the Cooper pairs tunneling through the insulating layer into the other superconductor without any voltage running through the device. This is similar to quantum mechanical tunneling of electrons through a potential barrier. The current due to this tunneling is proportional to the phase difference between the Cooper pairs on either side of the junction. This no voltage current relationship is called the DC-Josephson relation. In case of a biasing voltage, the current picks up a time dependence like this and oscillates and is thus called AC-Josephson effect. There is a critical current that this device is able to hold and it depends on the geometry of the junction, choice of material and operating temperature of device. In 1964, the DC squid was invented at Ford Research Labs. To construct a DC squid, we take two superconducting half rings and collect them via insulating layers, creating two Josephson junctions in parallel. The critical currents at both the junctions are equal. Now, we attach leads on both the sides and pass current through one lead. By Kirchhoff's law, the total current entering and exiting the system must be the same. This applied current goes halfway on one side and half on the other side, so effectively making the maximum allowed current in the device that can show Josephson effect equal to twice the critical current of the junction. By applying the magnetic flux through the device, we establish a phase difference between opposite sides of the ring. A circulating current appears due to this applied flux and supports the applied current in one arc and opposes the current in the other arc. Current flux relations. This is where the quantization of magnetic flux comes into play. The circulating current will increase proportionally with the applied flux up to a point corresponding to half the quanta. Since the circulating current is proportional to the energy, at this point it is energetically favorable to reverse the direction and maintain the same magnitude and once again restoring the original state at exactly one integer value of the quanta. Since there is a phase mismatch between the two Josephson junctions, a positive circulating current will cause the lower side of the ring to reach the critical current just before the opposite side. This oscillatory behavior is calculated to be of the form of a cosine function of the applied flux. We see that this oscillation is shown in the graph where, as expected, at 0 and at integral multiples of flux the current is maximum, while at half integral values it is 0. This behavior is periodic and persists with higher values of applied flux. Practical SQUID. Measurement of flux. This shows a practical DC SQUID where the voltage measurement is taken across the lead. With this voltage measurement, we can plot a current versus voltage graph. We see for zero flux, we get a characteristic IV curve corresponding to the maximum current at zero voltage. But when we apply the magnetic flux, we get the other curve corresponding to minimum current for one half of flux quantum. If we apply a biased current through the device so that we are sticking strictly to this line, we see that the voltage moves back and forth between the minimum and integer values and maximum at half integer values. Exactly as predicted, the voltage inside this device has a period of one flux quantum with maxima at half integer value and minima at integer values. This behavior closely resembles interference experiments in wave optics and hence is the final piece in the SQUID acronym, that is the interference. Generally, the quantum effects are difficult to see in real life cases, but in SQUIDs, we can already see that. For some times, we refer to this as macroscopic quantum interface. Applications and devices. The SQUID was designed to measure extremely small changes in flux as we saw on previous slides. The change in flux corresponds to a change in voltage. The direct measurement of small flux values was extremely difficult in the past and hence limited the resolution of our experiment. But the small voltage measurements through SQUID can be made by any conventional electronic. SQUID is the most sensitive kind of detector that can detect magnetic fields of the order of 10 to the power minus 12 Tesla. This is the energy equivalent of moving an electron by 1 millimeter in Earth's magnetic field. Being a quantum device, SQUID is only limited by quantum uncertainty principle. The variety of instrument can be made using SQUID as sensors, such as magnetometer, which through a series of pickup coils and flux transformers is used to measure magnetization of thin films and bulk materials. SQUID based voltmeters are extremely sensitive and can measure voltages of the order of 10 to the power minus 14 volt, and gradiometers that can also measure small changes in the gradients of the magnetic field. Thank you.